Hello everyone, and welcome. Today, we're diving into a breakthrough in AI architecture. We'll be exploring how to unlock the true scaling potential of large language models using mHC, or Manifold-Constrained Hyper-Connections. This is a comprehensive structural and infrastructural blueprint developed by DeepSeek-AI. To understand mHC, let's first look at how residual information flow has evolved. On the left, we have the standard residual connection. It's highly stable thanks to its identity mapping, but it strictly limits the network's cross-layer topological capacity. In the middle is the unconstrained hyperconnection, or HC. It expands the stream width to decouple capacity from compute, which is great for performance, but it fundamentally destroys identity mapping, causing catastrophic signal explosions. Finally, on the right, we have our solution, Manifold-Constrained HC. It projects this expanded topological capacity onto a defined manifold, restoring mathematical conservation and guaranteeing perfect stability at scale. Let's break down these differences in a simple matrix. While both legacy HC and mHC expand the residual stream width to n times c and offer a dense, complex connection topology, that's where the similarities end. Legacy HC destroys identity mapping and suffers from exploding or vanishing signals, alongside severe hardware and I/O overhead that scales with n. mHC, on the other hand, restores the identity mapping, guarantees strictly bounded forward and backward stability, and optimizes hardware overhead to be virtually negligible. Why exactly did legacy HC fail at scale? It comes down to two fatal flaws. First is algorithmic instability. Because the composite mappings are unconstrained, they cause exponential signal amplification, leading to massive gradient explosions, with gain magnitudes peaking at around 3000 during large-scale training. Second is the memory wall. The expanded multi-stream channels trigger severe memory access costs, increasing I/O overhead by 5n plus 1 c. This creates massive communication bubbles that completely destroy training throughput. So, how do we fix this? The answer lies in a mathematical cure using the Birkhoff polytope projection. By applying the Sinkhorn-Knopp algorithm for 20 iterations, we transform the residual mapping. This gives us three superpowers. First, norm preservation, where the spectral norm is strictly bounded by 1, permanently eliminating gradient explosions. Second, compositional closure, meaning multiplying these matrices across layers always yields another stable matrix. And third, it acts as a convex combination, allowing the network to optimally mix features across streams without amplifying the signal. Let's visualize how this perfect conservation actually works using a doubly stochastic matrix. Imagine an n equals 4 stream matrix. Because of our manifold projection, the row sum is exactly 1.0, meaning the forward signal is perfectly conserved. At the same time, the column sum is also exactly 1.0, conserving the backward gradient. By alternately rescaling rows and columns, this matrix acts as a perfect geometric volume regulator. The exact amount of signal energy that enters the matrix is the exact amount that exits, completely preventing any structural attenuation or amplification. When we plot signal amplitude over the depth of the network, the impact is striking. The orange line represents unconstrained HC. As you move deeper into the network, the signal wildly fluctuates and explodes. But look at the blue channel representing constrained mHC. The identity mapping is mathematically restored. Signals travel safely across arbitrary network depths, beautifully bounded, without ever exploding or vanishing. We can also see this in a thermal map of composite network stability. On the left, legacy HC shows massive gradient variance ranging from -498.5 to +509.1, creating extreme, unstable focal points that shatter forward propagation. On the right, mHC maintains a perfectly balanced, uniform weight distribution, tightly bounding the variance between 0.17 and 0.34. We've empirically reduced the maximum gain magnitude by 3 orders of magnitude. Now, let's talk systems engineering. How did we solve the memory wall? Through selective recomputing. Instead of naively storing massive intermediate multi-stream activations, mHC simply discards them. Using custom tile-Lang mixed precision kernels that fuse operations and reorder RMS norm, we only store the initial input for a block of layers. We then recompute the transient activations on the fly during the backward pass within mathematically optimal block sizes. To further optimize, we implemented dual pipe overlap to hide communication latency. By executing the MLP residual mHC kernels on a dedicated high-priority compute stream and avoiding persistent attention kernels, we achieved zero stalls. mHC flawlessly overlaps pipeline scale-out communication, allowing the hardware to execute compute and I/O simultaneously. This brings us to the core philosophy of mHC: theory meets iron. On one side, we have elegant algorithmic math, Birkhoff polytope constraints guaranteeing perfect signal conservation. On the other, relentless systems engineering, tile-Lang kernels, optimal recomputation, and dual pipe overlap. Mathematical constraints allow the architecture to converge, while custom infrastructure allows it to run fast enough to actually matter. The result? We achieved all this with only a tiny 6.7% overhead at the 27 billion parameter scale. And the empirical proof at that 27B scale is undeniable. First, training stability is pristine. mHC completely eliminates the gradient explosions seen in legacy HC. Second, it fundamentally elevates reasoning capabilities, showing a plus 2.1% bump on the BBH benchmark and plus 2.3% on drop. Finally, it drives global convergence, providing a systematic absolute loss reduction of 0.021 compared to the standard baseline. Most importantly, this isn't just a trick for smaller models, it scales robustly. Looking at our compute scaling curve from 3B up to 27B parameters, the architectural advantage of mHC does not attenuate, it holds strong even at exponentially higher compute budgets. And on the token scaling curve, tracking up to 1 trillion training tokens, mHC shows a consistent, sustained divergence from the baseline, proving its superior learning efficiency over time. To wrap up, mHC provides a verified, new blueprint for next-generation foundational architectures. We've proven that network topologies can be significantly widened without proportional flop penalties, successfully decoupling capacity from compute. We've also shown that to survive at scale, macroarchitecture innovations absolutely require rigorous geometric constraints. Ultimately, co-designing theoretical algorithms alongside GPU infrastructure is no longer just optional, it is strictly required to breach the memory wall. Thank you for watching.